Okay, folks, for week one of statistical concepts, our big topics is a lot of vocabulary and some definitions of processes that we need to go through. So we're going to look here, chapter one, section one, we're looking at sampling. Main things in this chapter, we're looking at constructing a proper sample and then defining different types of samples and then some of the more basic vocabulary. So let's look at some of the terminology. Statistics. What is a statistic? Well, a statistic is nothing more than, statistics in general is nothing more than the process of studying, collecting information to describe a situation or a process or to draw conclusions from it. We actually have within statistics two different branches that we're going to look at. We have descriptive, which is that part of describing, collecting and describing. You gather information so that you're still kind of drawing a conclusion, but you're stating that based on our sample, we believe that the population has an average of whatever, or that this many percent of people in the United States live in poverty, or this many percent of the people have a second job, or whatever it is we're trying to study. So that's descriptive. Then there's inferential statistics. Inferential statistics is drawing that information to learn about something, but we're trying to go one step further. We're trying to use it to make a decision, draw a conclusion. I'm trying to decide, is this new drug better than the old drug? Design a statistical test so we can gather evidence and we can come to that conclusion. And we have to be careful. Inferential statistics involves being very careful about eliminating any outside factors that could influence our results, or making sure that our results are significant enough that it didn't just happen by chance, that they are real results. So a population is the entire collection of individuals which we're collecting information from. In other words, it is the group we want to learn about. Defining the population is really the first major step in statistics, and it's not as easy as it sounds. For example, let's say we want to try to predict who's going to win the presidential election coming up. Well, it sounds like we want to learn about the candidates, but we don't. It has really very little to do with the candidates. What we really want to learn about are the votes, because it's the votes that determine who's going to be the president. Well, and it's not the votes themselves, it's actually the people casting the votes, because you can't sample the votes because they don't exist yet. So you have to go to the source of those votes, which will be the people that can cast them. But again, are we looking at all registered voters in the United States that we want to study? Not really, because there's a large portion of them that aren't going to vote. So we're not worried about them. And then there's another portion that's going to register between now and the election, and we'd like to include them, but they're not part of the register. So what our population in that case really would be is all people who are going to vote in the next presidential election. But again, some of them don't even know whether they're going to vote or not. So defining that population is very, very tough. A sample is a subset of a population. In other words, it's a smaller group that we select from that population. And that's the ones that we actually observe and gather information from. Why do we collect samples? Well, there's several reasons why we collect samples. One is money. Often it's just way too expensive to try to gather information about a whole population. Time. It would be very difficult and time consuming to try to survey everybody that was going to vote in the next election. Population is not well defined, as we said. We don't know for sure who's going to vote. Some of them don't know for sure. There are people that may not be even legal to vote that may vote in the next election. There's always a few. So trying to define the actual population would be very difficult. Now, I've already said time, but I'm going to put in changes over time. The thing with the samples, it's meant to be a snapshot. We want to get a picture of what's going on right now. So if we get too large, if we're trying to take in too much information, the time it takes to bring in that information may be a factor. If I'm trying to survey voters on who they're going to vote for, I want to do it in a relatively short period of time. I mean, at the very most, a few days, usually less than that. Otherwise, if it stretches out too long, one candidate may say something that, or say something stupid, or say something really, really great that draws people in. But either way, something might happen that causes people to change their minds. So the first people that we surveyed may have already changed their mind on who they were going to vote for by the time we surveyed the last person. So we got to worry about that. You got to get done quickly enough that you get a true snapshot, that everybody is being surveyed under the same conditions, that nothing significant can happen in that period of time. Last thing I'm going to put up here is destructive. Obviously, surveying voters is not destructive, but statistics is used a lot in manufacturing for quality control. If I have a part that has to be able to withstand a certain amount of force, I need to test it to see how strong it is. Well, I'm going to take it out of the assembly and I'm going to put it in a machine. I'm not just going to put that force on it. I'm going to put a little bit extra force on it to see if it holds. So kind of that safety margin deal. Sometimes I'll just put force on it till it breaks and measure how much it took to break it. That's what's called destructive testing. Obviously, in that case, we would not want to test every part produced because the test destroys it. We would have nothing to sell. So we take a sample, we test them, and if they're all good, we're relatively confident that all the parts are good, even the ones that we didn't test. Okay, so let's talk about how do we construct a good sample. We talk here about simple random sample. What is a simple random sample? Well, let's mention here briefly size. Size of a population is represented by the capital letter N. Large N, that's the number of people or number of items that are in a population. Size of a sample is little n. That's how many items are in a particular sample. There's all sorts of little rules of thumb out there about how big the sample should be compared to the population and all that. We're not going to get into that right now. So a simple random sample. Random means that all members of the population have the same chance of being in the sample. So just plain random means each item or each individual has an equal chance of being in the sample. Well, simple random goes one step further. Simple random says all samples of size n have an equal chance of being likely. So not only does each individual have an equal chance, every possible sample of that size has an equal chance. Simple random sample, we thought it was the lottery. There's 10,000 lottery tickets are sold, 5 are drawn out as winners. Each possible group of 5 tickets has an equal chance because those tickets are just thrown into a bin and mixed up and drawn out. So not only does each ticket have a same chance, each group of 5 tickets has an equally likely chance. Okay, so let's look here. The physical education teacher wants to study the physical fitness of 20,000 students enrolled at her university. She obtains a list of all 20,000 students, numbers them 1 through 20,000, and uses a computer to a random number generator to generate 100 numbers, 100 random integers between 1 and 20,000. Then she invites the 100 students who correspond to those numbers to participate. Is this a random sample? Yes, it is a random sample because each member of the group has an equal chance of being chosen. Is it a simple random sample? Yeah, actually it is at its purest form because we just took every item in the population, assigned it some sort of number or code, put it in a bin and drew them out. The random number generator is equivalent to throwing them in a hat and drawing them out. So this is not only random, but it is simple random. Every possible group of 100 would have an equal chance. So the professor in the last example wants to now draw a sample of 50 students to fill a questionnaire about which sports they play. The professor's 10 o'clock class has 50 students, so she just gives them 20 minutes to do the survey, do the questionnaire. Is this simple random? No, it's not random. It's not simple random, and it is not even random because she chose a group. Well, I guess you got to be careful. It could be considered random if all of her classes were the same size and she randomly chose one class to survey, then there's a possibility that it could be random. But it is not simple random because all of the groups of size 50 do not have an equal chance, because there's no possible way, if she was just going to pick a single class to survey, there's no possible way that you could get a sample that had members from other different classes mixed together. So it's not simple random. So, samples of convenience. My guess would be that the sample above in that last example where the professor just gave out the questionnaires to the 50 students in their class was a sample of convenience. She needed 50 surveys and happened to notice there's 50 people in that class, so she conveniently gave them the questionnaires. Samples of convenience are not random, but there are certain times when they are acceptable. They're acceptable when, as I mentioned before, the population might be very difficult to define, or the population may be set up in certain ways so that portions of the population are hard to get to. Now, samples of convenience have several different levels. Convenience, of course, is the key word there. It's easy. I mean, one way of a sample of convenience is I just walk outside and the next 20 people I run into, I'm going to survey. That's very convenient because they're there and I can do it quickly and don't have to go searching for them or determine whether they're in the sample or not. They're just there and I survey them. But that's a very, very poor sample. Most likely to have some very, very skewed results. But there are other samples of convenience that are less likely to be skewed, that are still convenient. They're still not truly random or simple random, but they're not as poor. They still give us usable data. So let's say in some cases it's impossible to draw a sample from truly random way, so that we do the best we can do. We use some sort of a convenient method. Now there's a sample of convenience is not drawn from a well-defined random method. So that, like I said, just going out on the street and just grabbing the next 50 people or 20 people or whatever that walk by and asking them questions. As you can see, there's problems with that because I'm restricting myself to a region and people that happen to be there at the time I am. So it's very, very restricted, and a lot of factors could cause that to be a very biased sample. Well, let's say that we have an engineer here that has received a shipment of 1,000 bricks. The blocks have been delivered in a large pile. The engineer wants to investigate the crushing strength of the blocks. So it takes a sample of 10 blocks. Why would you not want to be able to draw a simple random sample here? Well, because of the way the pile is set, you don't want to dig through the pile to get to the middle of the pile. You'd rather take bricks around the outside because it's easy to get to. You don't want to have to move the whole pile to random. And then again, how are you going to number them and all that? You don't want to have to deal with that. So you're going to take a convenient sample. Here, it's reasonable to assume that the bricks are relatively uniform. And it's also reasonable to assume that their position in the pile does not affect their strength. So randomly selecting bricks from the outside of the pile to test should be adequate. It'd be different if you just, surveying voters and you only selected a certain region because it was close to you. In that case, political views vary greatly from one region to another. So there would be reason to believe that there's differences in that convenient sample. Here, like I said, there's no reason to believe that the location in the stack affects the strength of the brick, so it would be okay to do that. The problem with samples of convenience is they may differ systematically in some way from the population. That is what we call bias. Bias is its difference between the characteristics of the sample and the characteristics of the population. We try to eliminate as much intentional bias as we can, and we try to reduce the probability of bias. But we can never eliminate the probability of bias. There's always a possibility. The only way to completely eliminate bias would be to know everything about the population and to choose the sample to exactly represent that. But if you knew what's in the population, you wouldn't need the sample. So, I mean, we can never truly know whether a sample is biased or not because we will never truly know the characteristics of the population. The whole purpose of drawing the sample is to predict those characteristics. So we're looking for what we call a representative sample. A representative sample is a sample that the characteristics of the sample are very, very, very close, if not exactly the same as the characteristics of the population. So if half the population has a certain viewpoint, approximately half the sample has the same viewpoint. So if, like I was saying with the bricks, if there's reasonable to believe that there's no systematic differences, then it is okay to take a convenience sample. So other different sampling methods that are random but not simple random. All of these that are listed here correspond to that, except for the voluntary response sampling, which we'll talk about when we get to it. So a stratified sample. In a stratified sample, you divide the population up into groups, and then you randomly select an item from each group. The reason you do this, let's say you're looking at as a business and you have different customers. Well, you might have sporting goods, toys, other departments in your business, if you're looking at a retail store. You don't want to take a sample of customers that only shop in one department. You want to get a sample of customers that shop in each. So you might divide up your customers as, customers that are mainly sporting goods, customers that are mainly food, customers that are mainly toys, and then select some from each group so that you make sure that each group is represented. An example of this here, a company has 800 full-time employees and 200 part-time employees. If you're going to sample them about a preference, maybe you're looking at changing contract or something, you don't want to, especially here since there's 800 full-time, only 200 part-time, if you're taking a sample of 100 employees, there's a good chance that all of them may end up being full-time employees. And you want to make sure the part-time employees are represented. So you do 80 from the full-time and 20 from the part-time. That way you get the exact same proportion, exact same ratio of full to part-time in your sample as you do in the population. Now, it's random because each member of the employee group has the same chance of being selected. But it's not simply random because each group of 100 employees does not have the same chance. If it was simply random, like I said, there would be a possibility of getting all 100 of that sample out of full-time employees. But with the stratified sample, it eliminates that. And in this case, I would say that's probably better to not be simply random. That this random method is better than a simple random method. A cluster sample. You still divide the population into groups, but now rather than selecting from within each group, you select whole groups to do. This is done generally for, I don't want to say convenience, but it's done for cost. Let's say you want to survey, doing a telecommunications survey on what households in the city are interested in for TV services and so on, internet services. If you did a simple random sample of all households in the city, you'd be running, and you wanted to go and interview them in person, so you wanted to knock on their door and interview them. You'd be running all over the city to interview people. So what you do is just divide the city up by blocks, and then you randomly select different blocks to go survey. That way, you can go park on the block corner and walk down the block and survey the houses and come back. So you can catch a bunch of them at once without having to travel all over. It saves on expenses. It's still random, but it's not simple random. The simple random process would cause too much time and cost to make that work. So we use this random method of cluster sampling. Again, maybe not as representative of the population because you do have to be careful. You might get a cluster within a relatively affluent part of town. And so now you're getting this whole group, this whole block of people in that economic class, and that might not be representative of everybody in the city. So here's an example. To estimate the unemployment rate, the government agency draws a simple random sample of households in a country. Someone visits each household and asks how many adults live in the household and how many of them are employed. Well, here it actually is clustered. It's not simple random because even though you're visiting individual households that were simply randomly selected, there may be more than one adult in each household. So you're not looking for just a single adult. And here's a case where, again, clustering would be better statistically because how do you define which adult in the household is part? If you're only going to take one adult from the household, how do you define which one is the one you're looking for? So here you have all the households. You select your households, but within each household, you do survey every individual that is in there, every adult that is in that household. Systematic sampling is a spot where you randomly select a starting point, but then you let the system take over from there. So items are ordered, and then you might take select a random number, and you then choose, a random number between 50 and 100. So that you get your random number of 62 maybe, then you're going to select every 60-second item to sample. This works a lot in manufacturing. Again, that quality control. You may randomly choose that number between 50 and 100. Okay, so every 60-second item produced, I'm going to test it. Or what's more common is, let's say you have to test one in every 100 parts. So you'll randomly select a number between 0 or 1 and 100 at the beginning of the day. Let's say your number is 19. So that means every 100 parts, you're going to select the 19th. So you'll select part 19, part 119, part 219, and so on. So you randomly select a starting point, and then the system determines the rest of the sample after that. So your automobiles coming off assembly line has decided to draw a systematic sample for a detailed check of the steering system. The starting point will be the third car, then every fifth car after that. So again, you want to test every fifth car. You randomly select which one out of the first 5 you start with, and that's every fifth car after that. So every car, it's random. Every car has a chance of being selected depending on what's selected first, but it's not simple random because once the first car is selected, then the rest are determined by the system. So there is no way that 2 cars in a row could possibly be part of the sample. And here's just another illustration of that systematic sampling. Voluntary response samples. Unfortunately, this is all too common because we have the right to say no. On voluntary response, most of your phone surveys, if you get a phone call, I know a lot of people hang up on them. I'm guilty of doing it myself. So obviously they're not going to get any data from me. No matter how carefully they selected me to be part of that sample, I'm just not going to do it. So that's a voluntary response. Also, if you've been at a mall, good chance you've had somebody walk up to you with a clipboard and say, hey, would you be willing to participate in the sample? Sure, why not? Or whatever. But the thing is, voluntary response samples are always skewed. They're always a problem, partly because, one, you got to have time. I mean, if they walk up to you in the mall and you're really busy and you got to get going, you're going to say, no, I don't. Well, maybe busy people have different viewpoints on the topic than people that have spare time, a little more spare time do. So it might be an issue. Also, if someone walks up to me and asks a question about, I'm not a cat person, I'm a dog person. So I apologize to anybody who is a cat person. But they walk up to me and ask a question about, say, hey, we'd like to take a survey on cats or cat health or whatever. I don't care about cats. So I'm going to say, no, I really don't want to do it. But if I'm a cat lover and a cat fanatic, oh, well, yeah, if it's a topic I feel strongly about, I might be more likely to take time out of my day to go ahead and complete that for them. So that voluntary response is big. Also, it depends on who they think it's for. There's been political studies done where they send out letters, surveys to people on political topics, where they've sent out 500 surveys and envelopes that are labeled from the Democratic Party, and another 500 that are sent out in envelopes that are labeled from the Republican Party. And the it's the identical survey in there with just a mark on the corner of the page to indicate what envelope it was sent out in. And surprise, surprise, the ones that went out as the Democratic Party come back with much more liberal responses than those that were labeled Republican Party. Because if I'm a liberal person, if I get an envelope that says Wisconsin Republican Party or whatever state Republican Party, I'm going to toss it in the garbage. I'm not even going to open it up because I have no interest in their party. So things like that, letting them know who is giving the survey sometimes can affect who will participate in the survey. Okay, so another vocabulary term, what's the difference between statistics and parameters? Parameters are a statement or a conclusion that describe the population. A statistic is a statement or a conclusion that describes a sample. So let's say I do get a sample of 1,000 voters, and I find that 44% of them are going to vote for candidate A. That is a statistic. 44% of sample will vote for candidate A. Now my parameter, again, usually I don't know this exactly. Generally I'm using my statistics to estimate a parameter. So I might say less than half of all voters are going to vote for candidate A. It may or may not be true or accurate, but it is a statement about the population. Therefore, it is a parameter. Which of the following is a statistic and which is a parameter? So 57% of teachers at Central High School are female. Well, are they saying 57% of teachers surveyed or teachers polled or anything like that? No, they're saying 57% of all teachers at Central High are female. So that is a parameter. In a sample of 100 surgery patients who were given a new pain reliever, 78% of them reported significant pain relief. Well, it says right in here, a sample of 100 surgery patients. So that is a statistic. Statistics describe the sample. And there it is. There's a parameter and statistic. There's a solution for that last one. So finally, this is what we just went through in this PowerPoint, section 1.1. What is a statistic or what is statistics? It's that gathering of information to learn about a topic. Difference between population and sample. Population is the whole group. Sample is a smaller group that we're actually going to gather information from. Simple random, we've discussed that at length. Convenient samples, when is it okay? As we said, when we have reason to believe that there's no significant difference between the whole group and the smaller group that we're going to be able to draw from. And then all the other sampling methods. So I'm going to switch over to my next PowerPoint quick. I'm going to pause the recording here for just a second. Okay, I'm back. So here we're looking at section 2, types of data. So we've got our population. We've created our sample, determined our sample from our population. We've got to draw some data from it. Well, when we're drawing data from a population, we're asking some sort of a question. And that question really kind of outlines what our variable is. Our variable, our data, is the response to that question. So we ask, are you registered to vote? Well, answering yes, you're put in the category of people that are registered to vote. If you answer no, you're put in the category of people that are not registered to vote. So the variable there is whether you're registered to vote or not. And that's your answer to your question that we ask. So what we're really talking about, when we're talking about types of data, we're talking about types of answers we can have to that question that we are asking or proposing. So we need to understand the structure of a typical data set, distinguish between qualitative and quantitative, just the types of questions asked, distinguish between different levels of measurement within each type. So ordinal, nominal, and discrete and continuous. So let's move on from there. Understanding the structure of a typical data set. So in a typical data set, we're looking at the actual data that we draw. And that data is determined by the variables that we're looking at. And that variables are determined from the individuals that are in the group that we're studying in our sample. And then, of course, we have the whole set of information, the data set, it's the information that we've collected from, or the set of data, the set of information we've collected from. So qualitative and quantitative. This is an important distinction for us. Qualitative. The answer to the qualitative variable or qualitative question puts the response in a category. The example I always like to use is, what's your favorite color? Your favorite color, your response is going to be red, green, blue, black, whatever. And it's going to put you into a category, of categories being the colors. Most yes or no questions are qualitative. Do you support this new bill? Yes or no. Puts you in the category of supporting or not supporting. Quantitative is numerical. There's a big division in the numerical variables that we'll look at in a minute. You might ask, how many children do you have? Your answer to that question is going to be a number. That puts you in a quantitative variable. How tall are you? Your answer is going to be a number. So this puts you into a quantitative variable. You're answering a number to the question. So for qualitative variables, as we said, they classify individuals into categories. Qualitative is often called categorical data. Quantitative, you're looking at how much, how many, or how big something is. So which of the following are qualitative and quantitative? A person's age. Your response is going to be a number. That will be quantitative. I should put quant. Person's gender. That's going to put you into a category. That will be qualitative. Mileage in miles per gallon. That will be quantitative. That's a number. Color of a car. That will be qualitative. Put you into the category. Okay, so now we got some items here to define. Following variables are qualitative. Person's gender and the color of the car, obviously. They put you into those categories. Following variables are quantitative, the person's age and the mileage received. So now let's look closely at our qualitative variables. Our qualitative variables can be divided into two categories, two different levels of measurement. Nominal and ordinal. Nominal means they can be divided up by name only. Most yes or no questions are nominal. Favorite color is nominal. There's no way to put them in order. Ordinal has some sort of a natural order. If they ask you what size shirt do you wear, you could answer small, medium, large, extra large, so on. So even though your answer to the question is still putting you into a category, you can rearrange those categories in order. I mean, large is bigger than medium, and medium is bigger than small, and extra large is bigger than large. So they can be put in order. So they would be ordinal. Quantitative variables. So ordinal variables have a natural order to them. And nominal has no natural order. And like I said, by name only. So state of residence, that would be nominal because there's no way of putting them better to worse. Gender, nominal. Letter grade and statistics class, it's still categorical. It's still a qualitative variable. But most people would agree A is better than a B and B is better than a C and so on. Size of a soft drink ordered at a fast food restaurant, small, medium, and large. It's just like we were talking about with the shirts. You can go from smallest to largest. So letter grades and size of the soft drink are ordinal. State of residence in general are nominal. So now let's look at our quantitative variables and the difference that we have there. Quantitative variables can be discrete or continuous. Discrete are things that can be counted. How many cars do you have? How many classes are you taking this semester? How many children do you have? Those are things you would count. Continuous are items that are measured. How tall are you? How long does it take to complete this task? Stuff like that. Those are continuous because measuring it, no matter how close together two things are, if you get down to a small enough unit of measurement, you can always distinguish the difference. You can find a difference between them. So when talking about continuous, no two things are exactly alike or exactly the same size because if you get small enough units of measure, you can always distinguish between the size of two things. So discrete, as we said, are those that can be listed or counted. Continuous, they cannot be taken as individual values because no two are ever exactly alike. So we have to group them together in intervals. So which of the following are discrete, which are continuous? Age of a person at his or her last birthday. That would be discrete. The key there is they said at their last birthday. So that means it's going to be 1, 2, 3, 4, 5, not 1.7 years or anything like that. It's at their last birthday, so it's going to be a whole number. The height of a person, that is continuous. So I'll label this as discrete. This one is continuous, because no matter how close, it's going to be measured for one, so that's our hint that it's continuous. And no matter how close two people are in height, there's always going to be a distinguishable difference if you get to a more precise measurement. Number of siblings, that's discrete. You're going to count the number of siblings you have. Distance a person commutes to work, that is continuous. Again, distances can have an infinite number of variations in length. So the following examples were discrete. Age at the last birthday and number of siblings. And continuous, person's height and the distance they commute. So here you've looked at the structure of data, different, defining what is the question and what is the data, what is the variable, and then looking at different types, qualitative and quantitative, and then the levels of measurement within each of those. So that's everything from section 2 of chapter 1. I'm going to change the PowerPoint quick, so I'm going to pause and I'll be right back. Okay, so here we are with section 3. We'll get designing experiments now. So we need to be able to distinguish between randomized experiments and observational studies. Randomized experiments are we actually create a condition and we give that condition to one group or another, and we create the conditions in which they're being tested. Observational studies, we just have to watch and see what we can see. Advantages of randomized experiments, advantages and disadvantages, of course. Understand how confounding can affect things. Confounding is a huge thing. That's when outside issues affect our data, and we'll talk about that. And then describe various types of observational studies. So let's take a look at randomized experiments versus observational studies. And experimental units are individuals who are being studied. These can be people, animals, plants, things, whatever it is that we're going to take measurements of or count or observe and take data from. Often called subjects. The outcome or the response is what is measured on each experimental unit. So each outcome or response, there's one for each individual unit, each item that we are studying in our sample. The treatment is a procedure that is applied to each experimental unit. Treatment is generally part of the experimental design. Drug testing, one group would get the new drug, one group would get the old drug. So let's suppose that a scientist wanted to determine which of the 3 types of seed will result in a largest wheat yield. So studies conducted as follows. Prepare 3 identical sized plots of land with similar soil types. Plant each type of seed in a different plot, choosing the plots at random. Water and fertilize it the same way. Harvest the wheat and measure the amount grown in each plot. If one type of seed produces substantially more, then it can be declared clearly better than the others. So experimental units are the plots of land, not the seeds themselves, but it's the plots of land. That's what we're testing, is the yield of crop from each plot of land. The treatments now are the types of seeds. The difference, everything on the plot of land is being held the same. Type of soil, how much water, how much fertilizer they get, what's worked with the soil is held the same. What's different from each experimental unit to the next is the type of seed that is put into it. So that is our treatment. And then, of course, the outcome is the amount of growth in each plot. So a randomized experiment is a study in which the investigator assigns treatments to experimental units. So the seed experiment described is a randomized experiment. We chose the seeds to give to put on each plot of land. An observational study is one in which the assignment of treatment groups is not made by the investigator. So nature or some sort of other circumstance assigns the treatment groups. You might observe people in social settings of someone who's a psychology major and somebody who's not. So you didn't necessarily choose the people, but you observed them and put them into the appropriate category and grouped their observations together. So let's do an example of an observational study. A study is performed to determine how smoking affects people's health. In this study, people cannot be, you can't force somebody to smoke, right? So you can't assign them that you're going to be in the smoking group. And instead, you take people that are already in that group and compare it to people that are already not in that group because they don't smoke. Because the assignment of treatments is not made by the investigator, it is an observational study. So, an example of a randomized experiment. Scientists report the results of a study to determine whether a new drug, I'm not even going to pronounce it, is effective in reducing levels of virus in patients with HIV. These patients were divided into two groups. One was given the new drug and the other was given a placebo. Now here you might say, well, isn't that kind of unethical to give someone a placebo when they think they might be getting medicine? In a place like that, they're very careful that they sign the papers up front that they know that there's a possibility they might not receive any treatment. So it was decided to examine subjects after 16 weeks and measure the levels of the virus in their blood. Thus, the outcome of the experiment was number of copies of the virus. So the treatments here are each people, or sorry, not treatments, the experimental units are each person in the study. The treatments are, did they get the drug or the placebo? Then, of course, the data is the amount of virus in their blood. Patients were considered to have a successful outcome if they had less than 50 copies of the virus per milliliter of blood. So in the group with the medication, 62% of the subjects had a successful outcome and only 35% in the placebo group. Now we have to look at how many were studied and all sorts of things to decide whether that difference is significant enough or if it could have just been random. And we'll talk about that later on in the course. We talk about blind experiments and double-blind experiments. Now, it's been proven through the years that it's very important that test subjects not know whether they're getting the drug or a placebo, because if they know they're getting the placebo, they might not try as hard to be healthy, work out, or eat well, or whatever. Or even the psychological factors of knowing you're getting the placebo could drag you down and make your illness worse. So they have to make everybody believe that there's a good possibility they're getting the drug and they're going to get better, so that so you don't have that extra issue. Sometimes, however, even though the patients don't know whether they're getting the drug or not, if the people giving them their medication know, they might treat them different, and that might cause something that causes them to have different health issues depending on what group they're in. So in many cases, a third party loads up the pill, the pill cups, and the person that's handing out the pill cups to the patients, they don't even know whether there's medication or placebo in there. So the person that's interacting with the patients does not know what group the patient is in, so that they don't give any hints or treat them differently that may affect the results of the experiment. Confounding. Well, what confounding is an outside factor that comes in. Maybe if we're doing that drug test, maybe a group of our people is exposed to pneumonia, and they bring pneumonia back, and a large number of people in that group get sick with pneumonia, causes elevated virus levels, or they could possibly pass away. And that could change the results of the study. They may have passed away, but there were people that, had they not got that virus, they may have been people that would have improved. So that's a confounding result. It's an outside result that cannot be controlled under the experimental conditions. If you can control it, you do. If you can't, you have to account for it. And that's what confounding is, the stuff that we just cannot control, so we have to figure out how to account for it. So in observational studies, they're obviously less reliable in randomized experience, because in the randomized experience, we can do everything we can to eliminate confounding. Whether the certain things we can eliminate, like we can eliminate whether they step off the street curb and end up getting hit by a car or whatever. So, yeah, something might happen where this example here, we have the group that trying to test to see if heart attacks are more prevalent in the group that smokes. The smoking group may differ in other social aspects. So maybe they don't exercise as much because they smoke and it's harder for them to breathe. So that may cause an elevated rate of heart attacks. So maybe it was not the smoking that caused the heart attacks, but another confounding factor that just happened. It's linked to smoking, but it's not caused by smoking. Things like that. Or the fact that smokers now have to go outside to smoke, and maybe the shock of the temperature going out when it's cold causes strain on their heart or whatever. So it may not be linked to the smoking directly. So it's something we cannot control, and it's impossible. The key thing for a confounding factor is that it cannot possibly be separated from the other treatments so that we can tell what was caused by this outside factor and what was caused by the actual treatments. So let's say our confounding. In the preceding example, a major problem with observational studies is it's difficult to tell what difference is in outcomes due to the treatment and what is due to between the control groups. So this is known as confounding. Gender may be a confounding. Let's say that men are more likely to smoke than women. Well, men are also more likely to have heart attacks. So there again, it's both things, the heart attacks and the smoking, were caused, I don't want to say caused, but linked to the variable of being male. So it wasn't that the smoking caused the heart attacks. Both the heart attacks and the smoking were caused by a third factor. And so there appeared to be a link between them, but there really was not. They weren't linked to each other. They were both linked to a single confounding factor. So let's look at the effects of blood pressure on health. A large group of people of all ages were given regular blood pressure checkups for a period of 1 year. It was found that people with high blood pressure were more likely to develop cancer than people with lower blood pressure. How might this be confounded? Well, people with high blood pressure may have other factors in their life, like smoking, that causes their blood pressure to be high, that also may be causing cancer. High stress might cause blood pressure to be high, which could cause cancer. Lack of exercise could cause elevated blood pressure, which could lead to cancer. So the book's example here, older people tend to have higher blood pressure, and their older people are also more likely to get cancer. So there's another possible confounding factor. We can't link whether it was the age or the actual blood pressure that caused the issues. So we're going to look at different types of observational study here quick. We have cohort studies and case control studies. And cohort studies can be divided into prospective, cross-sectional, and retrospective. We really don't use these a whole lot. This is in terms that are going to be really important for us in the course. But a cohort study is really just a group of subjects that study to determine whether various factors of interest are associated with a certain outcome. And the subjects are just followed over time. The subjects are just looked at a given instance in time and see what they can connect. In a prospective cohort, they're followed over time to see how these factors develop over time. One of the most famous ones, they're talking about the Framingham Heart Study, where it began in 1948 of over 5,200 men and women in Massachusetts, and every 2 years they were given a physical exam for heart health and discovered the factors that increased the heart disease within them. So again, that's a prospective cohort that's done over time. Cross-sectional cohort study is one that measures are taking at one single point in time. So it's cross-sectional versus sometimes called time series is the overtime. It's a perspective. So a retrospective is where you're looking at data that already exists. The subjects may already be long gone, but you're just looking at data that was already recorded by someone else and analyzing it to see what you can conclude from it. Maybe looking at it in terms of something other than what they were actually trying to study at the time. In a case control study, 2 samples are drawn. One sample consists of people who have the disease of interest, and the other consists of people who do not have the same disease. They're called the controls. Then the investigator looks back in time to determine whether a factor of interest determines which group they're in. So you've got people that have this condition and people that do not. You look into their past to see if those that have the condition have something in common that might have caused them to have that condition. And then check to see if that is not existence in those that didn't develop the condition. So you can see it's not as precise as an experimental study. So these are just some examples of case control studies. You can read through those if you want to. If you want to pause the recording to read through them, that's fine. So then what we saw here in section 1.3 is we saw the difference between randomized experiments and observational studies, the advantages of the randomized experiments, confounding and how it can affect things. I mean, it can affect an experimental study as well as an observational. It's just more common in observational studies because we're controlling less of the variables. I mean, it's easier for extraneous variables to get in there because we're not under control. In a randomized experiment, we're trying to control as much as we can. There are still some slight confounding factors that can slip through. Then, of course, there are different types of observational studies. And again, you don't have to worry about memorizing different types of observational studies because that's not something we're going to be really detailed on. We're not going to test on that. Okay, I'm going to open up the next PowerPoint, so I'm going to pause for one more second again. Okay, so on to section 4, which is a very important section here, talking about bias in studies. I mentioned that word bias earlier. About bias is difference in the characteristics of the sample compared to the characteristics of the population. And the whole process of selecting a sample is supposedly to try to limit the chances of bias. Now notice how I worded that. I didn't say eliminate bias because we can't eliminate it. There's always going to be slight differences. So I can't even say limit bias because we can never be sure whether a sample is biased or not. In order to be sure, in order to know whether a sample is biased, we have to know the characteristics of the population. And if we know the characteristics of the population, there is no point in taking a sample because there's nothing to learn. So the way we word it is we're trying to eliminate the possibility, the probability of bias. So make it as unlikely as possible to be biased, but it's still always going to be possible. So what is bias? As I said, bias is the difference between the properties of the sample compared to the properties of the population. Imagine you were to draw a simple random sample of students at a certain college to estimate the percentage of students who are Democrats. Your sample would probably contain a somewhat larger or smaller percentage of Democrats than the entire population of students, just by random chance. However, imagine drawing many simple random samples. How would you have? Some would have too many Democrats and some would have too few. So basically what they're saying here is if to be a good random sample, each individual sample may be slightly different than the population. But if you took several random samples, the conglomeration of them over time would, the average of those over time would average out to be about, well, would be average out to be equal to the proportion in the population. This is actually something called sampling distributions, which is going to be a big topic in about week 4 or 5 of the course. So we're going to come back to that. But basically saying is that it's not a systematic bias. A systematic bias, every sample that we took would lean one direction. So that would be a systematic bias. If every sample we could take using that method would always have more Democrats, a higher proportion of Democrats than there are in the population, then it's a bad sampling technique. But if on average, some samples would have too many, some samples would have too few, and on average it equal out to about the same, then it's an unbiased sampling technique. So you can't just say it's biased because it was slightly different. It's the technique, it was the process that's got to be biased or unbiased. So in a bias study, now imagine that you tried to estimate the percentage of Democrats in the population by selecting students who attained a speech made by a Democratic politician. So they attended this speech by a Democratic politician. Well, chances are they're more likely to be Democratic. So there's a systematic bias. That sample, no matter how you draw it, if you're drawing it from that group, is more likely to have a large number of Democratic supporters in it. So that is a biased sample. That is a systematic bias there. So sources of bias, again, choosing from a limited sample. Generally, samples of convenience produce bias because of, if they're convenient, usually there's some sort of defining factor that makes them convenient. Voluntary responses are always biased because, as we said, unless it's something you have a strong opinion on, many times you do not respond. Self-interest bias, sometimes you're going to, rather than give an honest answer, you're going to give the answer that you think someone wants to hear, or you're going to give the answer that you think is going to benefit yourself the most. So there's self-interest bias. I'll let you read through their examples. Social acceptability bias. if you're asked, did you vote in the last presidential election? Well, maybe you were busy at work and you worked late and you ran out of time. By the time you were done work, the polls were closed. You didn't vote. But you don't want to tell people you didn't vote because you don't want to look socially irresponsible, or you don't want to be looked down upon. Or maybe you work in a place where everybody's heavily Democratic and you voted Republican, and you don't want to admit that you voted Republican because you don't want to cause arguments or whatever at work. So you're going to have that bias. You're going to, in order to fit in, you're going to say something that's maybe not true or change your opinion. Leading question bias. Now this is huge when you're dealing with surveys. The question I'm going to put here is taxes. Do you favor decreasing taxes, lowering taxes? There's a question that's very cold. Some people say yes, some will say no. But if you word it as, do you favor decreasing the heavy tax burden on middle-class families? Well, a good share of the people are going to say yes, because, well, burdening middle-class families, that's not good. So if we can decrease that, yeah, let's do that. And if it says it's heavy, it's already heavy, so they must be struggling. So let's do it. Let's make it easier by decreasing that burden. So you might ask, they're giving the better way of, what is your opinion of decreasing taxes for middle-class families? So they're not wording it as a burden. They're not saying it's heavy. I'm just saying, hey, would you be in favor of decreasing taxes for middle-class families? Another thing that often causes biases in questions is attaching it to something else, like for maybe the school lunch program. Saying something about if it meant that your kids could have better lunch at school, would you be in favor of a slight tax increase? Well, most people say, yeah, for better lunch, I'll pay a few extra bucks a year. But if you start out with, would you be in favor of paying more in taxes in order to fund school lunches? Well, now they let it off with paying more in taxes, and your mind tends to latch onto that first thing it hears and not even hear the rest of the question. If you lead off with giving our kids better lunches at school, that's a positive thing. You've got a positive thought in your head. If you lead off with paying more in taxes, there's a negative connotation. There's negative thoughts in your head already. So the non-response bias, so people, if they can choose not to respond, well then those who don't respond, in many cases they have opinions that they can tell do not fit in with the interviewer or the circumstance they're in, so they refuse to answer because they don't want to cause that conflict. So you can see sampling bias occurs when members of the population, certain members of the population are more likely to be included in the sample than others. And those members have a certain characteristic that makes them more likely to be in that sample. So what is a bias study? A bias study does not necessarily mean you get the results that are different than what the population is. A bias study just means that there's something systematically in the system that causes it more likely to get results that are different than the population. And we've looked at all many of the different sources of bias. There's also the interviewer bias of you can say the words but have a facial expression, or the emotion you put into the words portrays some sort of a message to the person you're interviewing. Maybe when you give the two options of, are you in favor of candidate A or the mean candidate B? Just inflections in their voice and how they say it can cause issues. So there are a lot of other sources of bias that we didn't cover, but we covered the main ones. Okay, that concludes everything for week 1, chapter 1. So I'm going to end this recording and post it out there for you. If you have any questions, let me know and I'll get back to you as soon as I can.